You may have already encountered two classes of PDEs, the heat equation and the wave equation. We will now encounter the third and for now the last important class of PDEs, the Laplace equation. What is a Laplace equation? And where do we encounter this equation in application? That's what you will learn in this video. So what is a Laplace equation? We take the gradient of u and then its divergence, denoted as what's called delta u, and we set this to 0. That is what the Laplace equation is. So in 1D, that's easy, that's just ux equals 0. And what does it mean in 2D? Well, the gradient of u is the vector with ux and ui. If you take its divergence, you take the ddx of ux equals uxx plus the ddy of ui plus uyy equals 0. So in 1D, Laplace equation is just uxx equals 0. 2D, uxx plus uyy equals 0. 3D, uxx plus uyy plus uzz equals 0. That is our PDE. All of this in rectangular coordinates, of course. So why is this equation important for us? Well, there are several applications. For example, we can look at the heat equation, which is ut equals alpha squared delta u. If you are in steady state, ut equals 0, so we get alpha squared times delta u equals 0, so then we have Laplace u equals 0. So Laplace equation is actually sort of a special case of the heat equation once we are in steady state. But we encounter it more frequently if you look at the flow field, where u is the velocity of the flow. If this flow is irrotational, so no vortices, then we can write u as the gradient of some phi. U equals gradient of phi. If furthermore our flow is incompressible, which is very often the case, we have divergence of u equals 0. If you combine this, we get the divergence of the gradient of phi equals 0, or Laplacian phi equals 0. So here again we have our Laplace equation. If you find phi, we have our flow field. Third application, when we look at Maxwell's equations, we have divergence of the electric field equals density over epsilon 0, rotation of the electric field equals minus dB dt. Now, once dB dt equals 0, which is many applications, our electric field is irrotational, which means that you can write this as the gradient of phi. It's usually written as minus the gradient of the electric potential. And then plug it in here. In the case we have no free charges, rho equals 0, we have again Laplacian phi equals 0. So again we have the Laplace equation. So that is why this equation is so important for us. It occurs in many fields of physics. Now, Laplace equation does not contain a time derivative, so we do not need initial conditions. We do need boundary conditions though. So how many do we need? Well, you can take a look compared to the heat equation. So our domain will have some boundary. We have to specify some boundary condition there, similar to the heat equation. For example, we can give Dirichlet boundary conditions. Then we specify u on the boundary, and inside our domain Laplacian u equals 0. Or we can specify something else on the boundary, like Neumann conditions. You specify the normal derivative everywhere on the boundary, and your problem is fully specified. Or maybe something else. However, remember, these boundary conditions you impose are always dictated by the underlying physics. So the physics will tell you what boundary conditions you need to impose. And now you know how many you need in order to fully specify your Laplace problem.